while I am finishing taking record here.
Are we going to have another quicker question today?
We are going to have 8 more. Okay, so I did not see Megan. Yeah, okay, you're there. And Alina is here, and Caleb. Okay. And sitting next to Satish, who's now walking toward me, was Dylan, right? Cody Hagen, right? Dylan is you.
Yeah. I don't have my clicker, so can I run and grab it, or is it going to matter?
Go ahead, grab it. I'm still going to move forward.
Can I just write down the answers?
You still have one? No, we'll deal with it. But I mean, they still don't have them available. Is that the case? We'll deal with it. Oops, wrong thing. We only had 6 people that answered, and then I pressed the wrong button. I am restarting it, so everybody who answered, you need to answer again because I hit a wrong button. It wasn't intentional. I hit the keyboard by accident. Okay, the question is, how many mean solar days are in 1 year? We now have 8, which is 2 more than we had before. Any other clickers here?
Oh, no. Hold on. Yeah. Hold on.
Okay, while she's grabbing hers, I heard people talking about the homework question with energy and mass.
Yeah, that was hard. Oh.
And that problem is a problem about units, right? We haven't studied that equation. It's not about understanding the equation. It's about units. And so the standard units are what we need to use in the problem. So for mass, our standard unit is kilograms. And for distance, the standard unit is meters. And for time, the standard unit is seconds. So in this problem, we have mass. So we have this. And we have the speed of light. What is speed?
Meters per second.
It's distance covered per time, so units of meters per second. So we need to get C, the speed of light. Just remember that C is the speed of light, in units of meters per second.
So substitute for C M over S.
No, you need the number as well.
Well, I meant
But you
to
need-
look at the equation. Because what you're going to put in is going to be the speed of light, which is going to be meters over seconds.
Well, you can get the speed of light in other things. Like some people use the speed of light in miles per hour. I don't even know what that value is. But I know what it is in meters per second. But you need to make sure you use the value in units of meters per second. So I mean, the correct value is 299792458 meters per second. For the mass, we need kilograms. And they give us in the problem, the mass is, if the student who came by earlier today was correct, 3.10 grams. Gram is not kilogram. What's the difference in a gram and a kilogram?
Just 1,000.
Just 1,000. So you need to make that change so that you convert this into the correct number, and I'm not going to write the correct number, of kilograms. The reason I'm not writing it is because that's the actual only part besides punching numbers into a calculator of the question, is converting from grams to kilograms. And then you just put the numbers in your calculator and you get your answer. And the units for your answer, the energy will be in units of capital J, which stands for joules. And actually, when I write it out like that, I should put it as lowercase joules. Okay, so now that I've talked about that, hey, look, it's still open. Answer really quickly, Lauren Lee. Now I make her all panicky. I got it. Are you on the right channel? Good. All right. So now we have one more answer. 8 and 2. Those were our answers. How many mean solar days are in 1 year? The 8 are correct. It's not like I can lead you up to that. 365.2422. Now, just so you know the schedule, it's lab time. It's supposed to get dark, and ideally in an hour we'd go out and observe the sky. But it's also overcast, and you know what you see when it's overcast?
Nothing.
Nothing, unless you have William Herschel as your teacher. William Herschel, you may have heard of him, a musician. He was also the royal astronomer. He set up lanterns in his garden. He would just like aim, telescope the lantern, and then I think it was King George who would come and look and say, "Oh, look at what," you know. And he's just looking at fakes, which is kind of funny and interesting. But we're not going to look at fakes, as fun as it would be. So what I'm planning on doing is at 9 o'clock, if it's clear, we'll go out there. I don't think it will be. So I'm just going to, we'll take a break because nobody can sit for 3 hours and lecture. But we'll just take a break and then continue on and have a nice long lecture night. Yeah, I knew that would be really, really popular. Okay. We really are. I was not joking. Otherwise, we wouldn't be able to get 9 clicker questions in, right? That 365.2422 days. At the end of, well, before we get to the historian days, the very end, before we should break, if time works out the way I want to, we'll talk about calendars. And you guys know that we have a leap year system. Why do we have a leap year system?
To account for the 2.4.
To account for that 0.2422. So we have different calendars historically. Oldest calendars would have something like 365 days in a year. But if you have 365 days in a year, just about every 4 years, you're going to be 1 day off. How do they know it's 1 day off? Because you look at those important times we talked about last class period. We have things like the solstices and the equinoxes. The solstice and equinox are when the sun is at a certain position. In fact, you can describe the solstice, each solstice and equinox as a specific location on the celestial sphere. You have a homework question that asks you to do just that. So when you see the solstice occur at a different time on the, different day on the calendar, whoops, our calendar has moved. We don't get to set the time it takes for us to do an orbit around the sun. And our calendar is supposed to be marking that. And so we had, I think the Julian calendar was the one that introduced leap years. And the Julian calendar is probably the one you think we use. But it's not. So how do you think leap year works?
Once every 4 years besides years that are divisible by 400.
Okay, she knows a little bit more than most people. That's not perfect, but that's moving forward. Most people think that we have a leap year every 4 years. They think that every 4th year we add an extra day. And that's what the Julian calendar did. Now, Julian from Julius Caesar, right? That's a pretty old calendar. But when they realized that that wasn't right because it's not 365.25 days in a year. If you add an extra day every 4 years, you're using 365.25. So then you have, if you look at that 2422, you're adding 0.0078, yeah, 0.0078 extra days per year. And so you have to pull back. You have to say, okay, we're going to have to skip a leap year every now and then. And so the rule is you have a leap year where you add an extra day every 4 years, except if the year is divisible by 100. If the year is divisible by 100, you skip leap year. And now, if you think about it, have we had a year divisible by 100 recently? Yeah. To you guys, that may not seem recently. Like, my son was born, January 2, 2000. So, to him, that was infant times. And he's now sophomore in high school. But to me, that's like, last week. I was already a college professor. I've been a teacher for 5 years at that point. So it's real recent to me. That was a leap year. But the rule I just told you, you skip every 100 years. Every year that's divisible by 100, you skip the leap year. But it was a leap year for the year 2000. So then you say, what gives? Is teacher lying to me? And no, I'm not lying to you. There's another rule beyond that. Because if you skip one every 100 years, then you're down to 365.24 days in a year. And that's not right either. And so every 400 years, the rule that Lauren Lee had, it was working on, every 400 years you don't skip leap year. So every year that's divisible by 400, you don't skip leap year. And since 2000 is evenly divisible by 400, we didn't skip leap year then. Now that makes the year come out to 365.2425. It's still not perfect, but it's pretty close. We're going to have to wait a millennium before it's going to cause a problem. So that's what we actually used with the Gregorian calendar. So the calendar we're on now, named for Pope Gregory, the reason I can keep these straight is because I know the popes came after Julius Caesar, is the one that has the rules for leap year I just described, to try to take into account this 2422 as accurately as they can. And when that Gregorian calendar was adopted, depending on where you were, it was a different year, and thus a different potential number of days. But basically, you went to bed, and you woke up 10 days later, or 11 days later, depending on which country you're in, because they were adopted different times in different countries. Which is kind of cool, but they did that to try to bring the calendars back into a semblance of order. All of that from one slide that didn't have a picture on it. Let's move forward to a slide that does have a picture. Oh yeah, this doesn't have a picture. This is a calculation just like you've seen. Now I was working with a student on a homework problem that is somewhat similar to this. So let's look at that homework problem just real quick. You have a homework problem that says, what if, and I'm going to write down right now, 1 year is equal to currently 365.2422 days at 24 hours per day. Right? That's what 1 year is right now. But according to that homework problem, it says, what if the rotation of the Earth slows down so that a day just gets longer? So that we end up with 1 year. It's still going to be 1 year because a year is the time to orbit the sun. But the 1 year would be equal to 180 days at some unknown number of hours per day. And the question is, what is that number of hours? Well, I can't believe you're taking notes, Holly. Let's just ask Holly. What did we do? Why are the lights out behind you? Trying to figure out what's up with the lights. Okay. Somebody played around with the switches. The length of an hour is the same, yes. So it says don't make any strange things there. So we're just going to have more hours in a day. What did we do, Holly?
So we took the regular year, and then we multiplied that by 24, and then set that equal to 180.
Okay. What she said was one line below what I wrote. 1 year is 1 year, right? That's a given. It's still going to be the same amount of time to go around the sun. And so then we took the number of days, multiplied by the number of hours per day to get how many hours are in the year. And so we took 365.2422 days times 24 hours per day. So if you look at that, that's going to be days on top, days on bottom. If it was 5 on top and 5 on bottom, you say 5 divided by 5 is 1. If it's days on top and days on bottom, day divided by day is 1. And so that's just going to be hours. On the other side, we have 180 days times x hours per day. Once again, the days cancel. And so I have equations with hours equals hours. On this side here, I'm going to leave the numbers right now because well, first of all, I'm not going to give you the answer.
But it's not the same as the other one? Similar to...
I didn't understand you, Alina.
It's not similar problem, the same as the homework that we're doing for...
This is the homework. I am doing what's in the homework. But I'm not going to finish it. Right, so x, the number of hours in a day, is just going to be found by solving for x here. So I divided by 180. And so I'm not going to do the calculation because I want you to figure it out. And that's only half of it because that is how many hours there will be in a solar day. It also asks you to do a sidereal day. So you have to think about what's the difference in a solar day and a sidereal day. Specifically, how many sidereal days are there compared to solar days? And I will actually reiterate the answer to that later on, but I don't want to say it right here because I want people to have to think about and put pieces together. But then you just do the same calculation again. It's not a bad thing to think. It is a bad thing to wait. Time zones. Why do we have time zones?
Because we don't want the sun setting at noon.
Yeah, we want to have it so we basically have noon is when the sun is passing your meridian, plus or minus about an hour and a half. And so we have these different time zones. I think it's funny. About 2 hours ago, I posted on a little meme somebody posted to Facebook, Eddie Clayman. Eddie Clayman reposted a little thing that said, every day of your life except for 2 have 24 hours in it. And it's supposed to be some deep thought, like some goof. And I wrote back, clearly this person hasn't done much traveling. On my first wedding anniversary, there were 31 hours in that day, which is really kind of cool, right? Yeah, it's a special day. We had extra hours. How did we have extra hours? We were flying from Malaysia to California. And so we were crossing a bunch of time zones, and our day truly had way more than 24 hours in it.
Wow.
For somebody to post that, they have to, not have thought about what they were posting. Yeah, which it turns out a lot of people, I have met people here at Union College who've never seen the ocean.
Oh, wow.
Yeah, having grown up first on the coast of West Africa and then on the coast of California, well, that's a bizarre idea to me. Okay, so we have lots of different time zones for a specific reason, so we can kind of keep track of, it's noon, so the sun must be overhead, it's time to eat. Granted, my stomach would tell me it's time to eat no matter what, but that's beside the point. When you travel from one time zone to another, you can get jet lag. Why? Because your body develops a cycle and it knows when I'm going to get up and when I'm going to go to bed. And you travel to a different time zone, the sun rises at a different time, and your body says, oh, no, we don't. I used to get jet lag going from like the West Coast to the East Coast. And then I went to Japan for a summer. In college, we went on choir tour to England, which was awesome. Went to England. I felt nothing when we got to England because I was super excited. Came back after spring break going to school. How excited are you going to school after spring break? Yeah. I was like dying for 2 weeks at that point. Anyway, went to Japan. I got there and I was like, I know 3 in the morning, but I'm wide awake. So I'm out wandering around the streets of Japan. I finally come back and go to bed about 5 in the morning and wake up, in the afternoon. Really bad jet lag. But ever since, nothing. I apparently screwed up my body's clock so bad that traveling from time zone to time zone doesn't affect me anymore. Which is kind of cool, right?
Your body's internal clock said screw it.
Yeah, my body's internal clock said I'm out of here, yeah. And it never came back. It's just gone. Now, some interesting things to note here is that time zones are not just vertical lines on this. A vertical line would mean that it's following a line of longitude. And some of these follow the lines of longitude, like the prime meridian. That's a straight line. But then you have these other ones that do some funny things. Why? Often it's geopolitical borders, right? We're going to make our country so it's all in one if we can. So you look at Greenland up here. Greenland is, oh, excuse me. There's Greenland. Of course, Greenland's all in one time zone. Iceland's what I meant to say. Okay, so I did it right the first time?
Yeah.
Okay.
The big one that has a lot of ice on it is Greenland.
Yes.
The one that doesn't have a lot of ice on it.
I've been told that they intentionally named them that way so people would say, oh, I'm going to go to Greenland. Huh, there's nothing here but ice. Anyway, okay, so this one here, before I make myself look super, super stupid. It's really big. It covers many time zones you would think, but it's all in one time zone. And we have things like, in the United States, you can carve out well, let's not worry about it. There are some regions that are isolated in a different time zone. And of course, over here you have a really bizarre change, but that's working with the international date line so that you have a country that doesn't say, well, if you live on this little island, it's one day, and you live on this little island that's 5 miles away, it's a different day, but we're all the same country, because that would make life hard. And in fact, I don't remember the name of the country, but there's a country here where Seventh-day Adventists have just decided, okay, to be logical, we're going to keep the day that is Sunday because it works out with everybody around, for the other islands near them that aren't part of their country, that is Saturday. And so no matter what they did, they would have half the people around them saying you're keeping the wrong day. It's kind of just an interesting curiosity, right? The international date line is the opposite side of the Earth from the prime meridian. Now, in the sky, what's the equivalent to the prime meridian?
In the sky?
Yes.
It goes to your zenith.
Well, not through your zenith necessarily.
Oh, what's the equivalent of the prime meridian?
Yeah. The equivalent to the prime meridian is where we mark 0 latitude on Earth. In the sky, we measure it in right ascension. We mark 0 right ascension on the equinoctial calure. That's why we have to learn it. The equinoctial calure is actually the meridian that goes from the north celestial pole, of course, all meridians go from north celestial pole, south celestial pole, and passes through the vernal equinox. That is the location where the sun will cross the ecliptic, the sun path, will cross the equator on March 21 or so. That's actually what makes that meridian special. Okay, I am going to just move on from here. I think everybody's got an idea that there's international date line and so on. And we'll talk a little bit about the moon. How long is a month? That is on the calendar. Okay, 1 month on the calendar is equal to 28 days in poor little February up to 31 days. How did we get that for a month? The month, as the name implies, is based on the moon cycle. But the moon cycle, I have 29.531 days is the moon's synodic month. Synodic, not to be confused with cyanotic. Cyanotic means a cyanish color, bluish color. That's what happens when you don't have oxygen. Your skin turns cyanotic. The synodic month is the month as defined from new moon to new moon. So from new moon to new moon, it's 29.531 days. Now, how many rotations how many orbits does the moon do in one synodic month? How many orbits around the Earth? It's a little bit more than one. It's just like when we talked about the days for the Earth. Now, the moon has something really interesting. The moon, we say, is tidally locked. The same side of the moon is always facing the Earth. The reason is because the moon is not perfectly uniform, and the side that has slightly more mass has a slightly stronger pull from the Earth, and so over time, it's settled in so that is facing the Earth. And because that's facing the Earth, the moon has actually become distorted, so its core is not in the center, its core is actually pulled toward one side, and that's the side that's facing us. So the moon's not perfectly symmetric, and one side always faces us. I say it always faces us. There's a little bit of jitter in there, but we'll not worry about that. So the moon is just going around the Earth, constantly facing the Earth. So in 1 month, the moon is going like this, facing the Earth. Okay, so that's what's happening to the moon doing 1 month. Now, I just did one complete cycle, right? But while I was doing that, the Earth was going around the sun. So if the sun was out there when I started, the Earth has moved over like this, and now the sun is over in that direction. So the moon, in doing one orbit around the Earth, hasn't gotten yet to where it's pointing to the sun again, that same side. So it's not a full moon yet. It has to do more than one complete orbit to get to the position of a full moon. So the synodic period, the time from full moon to full moon, or new moon to new moon, to be technically correct, it's easier for me to imagine it full to full, and it's the same time period. So the synodic period is longer than the time for one revolution. So we have another term, we have the sidereal day, sidereal month. The synodic month is 29.531 days. The sidereal month, which is on the clicker question coming up. Actually, I'm just going to move this forward to the clicker question so I don't get it wrong, is 27.322 days.
Sidereal is...
With respect to the stars. What that means in a practical sense is it's the time for one actual 360-degree orbit or rotation. Now, we've already looked at, with our activities, the moon cycle. The cycle of phases of the moon is simply based on geometry. No matter where the moon is, roughly 1/2 is lit up by the sun. But where we are on Earth, if the side we see is not the side lit up by the sun, then we say it's a new moon. If we see it partially lit up, well, it's going to go from crescent and on. Now, the names of the moons are somewhat important to know here. They're very logical. New moon means it's dark. Crescent is shaped like a crescent. Waxing means it's growing. Notice the waxing crescent is complete circular on the right if you're looking above the horizon. Then you get to first quarter. So first quarter, you're 1/4 of the way through the full lunar cycle. That's why it's called first quarter. But it's a half moon. It can be confusing if you don't think about what the name means. You say first quarter. Well, how can that be half if it's quarter? Because a full moon is halfway through the cycle. Waxing gibbous comes in between. Then waning gibbous, that's where we are right now. Third quarter is again a half moon, but notice the difference. Opposite sides are the sides that are seeing the sunlight. And then finally we have waning crescent, and we get back to new. So that's the sequence of names for the moons. Did you have a question?
Yeah, like how often do each of these phases occur?
Well, each one occurs every 29.531 days, right? And it goes through. So if you take 29.531 and you divide it by 7 to get the quarters, it's just a little over 7 days for each quarter.
So each one appears in the night sky for 7 days?
Actually, from here to here is about 7. From here to here is about 7. From here to here is about 7. And then from here to starting over is about 7. So going in between these pictures is about,
In essence, it's only like a couple full moons a month.
On average, there's one full moon a month. In fact, we've all heard names for special moons. And we recently had a big thing about it's a blue moon, and something happens once in a blue moon. Well, a blue moon, there's a couple different definitions. It's not perfectly well defined, so you can find different ones. But one of the two basic definitions of a blue moon is a month when you have 2 full moons. The second, actually, it might be the first one in a month that has 2 full moons is called the blue moon. I now forgotten which one it is.
Pretty sure it's the second one. Yeah, you'd think it'd be the second.
You would think. I am pretty sure the other definition is a quarter, which is 3 months, that has 4 full moons. I'm pretty sure it's the third one out of the 4 is the blue one, not the fourth one out of the 4.
When I was reading in the book, I saw that they claim that sometimes the light that goes through the earth hits the atmosphere, and instead of scattering the light to where it filters out the blue, it actually lets it go through, and the moon looks more blue. And I was like,
I have never heard any good scientific description saying that the moon actually takes on a blue color. Yeah, red moons, we talked about that. I'm actually going to have the picture from the book on the red moon coming up. But the moon, a new moon can look red, an eclipse moon can look red because of the earth. And go ahead and just say when you find what you're looking for there, Ezekiel. Come on. So, our clicker question, the second one. A synodic month is 29.531 mean solar days long, while a sidereal month is only 27.322 mean solar days long. Why the difference?
Is it open?
Yeah, it's open. We have 6 responses so far. 7 now. We should have, there we go. Okay, so we have the same 9 that answered before. Oh, wait, Labor, do you have yours? There we go. So I'm just to make sure, I'm seeing responses from everyone but Satish, who doesn't have his with him,
No.
Sarah, who doesn't have hers, and Margaret, who doesn't have one. Right? Okay, so the answers we got here were 8, 2, and 0. Now, the correct answer is not A. The correct answer is B. And I wanted to put this in to make sure we followed along. Right, I talked about the sidereal days and the solar days, and in that case, the Earth does one more rotation, so it has one more sidereal day than it has solar days in a year. Now, with the month is also, I talked about how many days there are. As the Earth goes around the sun, the moon goes around the Earth, and the moon in one complete cycle, just like the Earth will have one extra rotation in a year than it had for its sidereal than for its synodic. And so the answer was actually there's one more sidereal month than synodic month in a year because of the orbit. So that one was a little tricky. I had to ask it to make sure people think about the differences.
It's worded difficultly.
It's worded difficultly?
Yes. As an English major, I can't figure that out.
Well,
I'm also really technical.
this one's months in a year, and this one is rotations in a month. And there is a partial additional rotation in a month, but not a full rotation.
So there's like 13 months.
Well, if you break it down, if you take the 29.531, I have to go to my calculator so I can give you the answer. Whoops. I got to start over because I can't write. 365.2422 divided by 29.531. So there are 12.368 synodic months in a year. And now just to make sure, because I didn't actually check this, I said, yeah, it's got to be that. 365.2422 divided by 27.322 is, yeah. It's always good to actually check to make sure my understanding was correct, right? Since I didn't check beforehand, I was like, well, yeah, it's got to be.
What did you take again to arrive at those numbers?
Yeah. Well, I did it on the calculator, and you couldn't see the calculator.
Yeah.
I did the number of days in a year divided by the number of days in a month. And then for this one here, I changed it,
Same thing,
but changing to the sidereal. Yeah.
Okay.
And so this is the one we care about, right? Because we notice full moon to full moon or new moon to new moon. So basically 12 and a third, a little bit more than 12 and a third months per year, which means that you should have a 13th month in a year approximately every 3 years, which means you're going to have a blue moon approximately every 3 years. So it's not that rare.
So speaking of blue moons, I found it.
Okay.
I was like, maybe I was just really sleepy and I'm making this stuff up. But no, it's on page 67 that they said that it might.
Remember, I don't actually have a book. They wouldn't.
Oh, well, the rest of it.
Yeah.
At the last paragraph says, it is possible, in fact, that on rare occasions the moon may look blue. This odd coloration can be caused by particles in the Earth's atmosphere. Normally, our atmosphere filters out blue colors and allows red passes through, which is why the sun looks red when it's low in the sky. However, if the atmosphere contains those particles whose size falls within a narrow range, the reverse may occur. Airborne particles from volcanic eruptions or in the smoke from forest fires occasionally are just the right size to filter out red light, allowing mainly the blue colors of the spectrum to pass through.
Okay.
So under these unusual circumstances, we might therefore see a...
Okay. But yeah,
But it's not the...
it's not an astronomical reason. It's simply if you have the right pollution, just the right pollution.
It's got to have the right stuff.
Yeah. Thank you. Okay, one last picture here to go with the moons. I put this here primarily for this picture right here. If we are in the northern hemisphere, then we look in a roughly southerly direction to see the moon, and we can see the phases, and we have the, well, this here is just showing the stage of the D, and so that would be a waxing. This one here is showing the stage of the G, that's the waning. And so we have the simple rule of, dog for, whoops, that's not going to help you at all, the Department of Defense. For waxing if it looks like a D, full if it looks like an O, and waning if it looks like a G. All right, moving on. Did anybody have a question about that whole dog thing? Seth?
Well, not about the dog, but more about the little diagram, because it looked like the arrows on the bottom picture were pointing from west to east.
This is showing where you would see the moon at sunset, depending on the phase. And so at sunset, of course, you only see a waxing moon at sunset. You don't see a waning moon at sunset.
Right.
And you only see a waning moon at sunrise. So dawn here, sunrise.
Okay.
So that's that motion you're seeing is where it is at that time. Well, if you're looking at the moon at sunrise, you're only going to see it when it is in the waning stages at sunrise. And if it's a full moon, it'll just be rising at sun or setting at sunrise. and you go later on in the cycle, and it's higher in the sky, and at the middle when it's the third quarter, and then it starts going down again. All right. Eclipses. I love this picture because it shows you the Earth. Did you have a question, sir? Or, no. I've been up since 5. I am also very tired. Yeah, and we'll take a break in about 20 minutes. I was at the gym by 5:30. Yeah, I'm proud of myself. Yes, I am. There was no reason for me to be up at that time except for, trying to make my lungs work. I really love this picture because you see what it looks like on the Earth when you have a solar eclipse. It's very dark here because it's not getting direct sunlight. It's like nighttime there. I'm going to erase my red dot. And the geometry we already talked about, you have to have the moon directly between, is that a question?
Yeah.
Directly between the sun and the Earth to have a solar eclipse. What's your question?
So, how often do these solar eclipses occur?
Solar eclipses will occur, I think it's a little less than twice a year. Right, because we had the pictures of our geometry. The moon is, well, let me go forward to that picture. I only put in one of these pictures. We'll see.
How often do solar eclipses last?
It depends on where you are and what the eclipse is.
So it would occur the second time when the Earth rotates to the opposite side of the sun?
Not the one I'm looking for. This is the one I was looking for. This shows the orbit of the moon around the Earth is inclined about 5 degrees from the orbit of the Earth around the sun. And so you can only have an eclipse when the moon's orbit is crossing the ecliptic.
Yeah.
And so those come, and they call them eclipse seasons, as we saw with the work. And they come, I think it's somewhere, I don't remember, but it's a little bit more than half a year apart, is my recollection.
Do the solar eclipses affect different parts of the Earth? Or wouldn't affect the same part twice in the year? Is that correct?
Yeah, that's correct. And each eclipse has a very specific pattern if it's a solar eclipse based on the path. The lunar eclipses are not nearly as exciting. They're just everywhere, right?
Yeah.
And you saw I had a picture that shows those in between. So I'll get to showing that picture. Just making sure everyone has the geometry here. The moon, the side facing us, is going to be in shadow, so it has to be a new moon to have a solar eclipse.
So then this means that the dark side of the moon isn't always dark.
Well,
We just never see
some
it.
people say there is no such thing as the dark side of the moon because all parts of the moon have light sometime. Right? As the moon goes around the sun, different parts of the moon will be lit up. The same side of the moon is always facing the Earth. Actually, not around, around the Earth. The same side of the moon is always facing the Earth. So when the moon is between us and the sun, it's the far side of the moon that's in daytime, that's lit up, and the side closest to us is the dark side. But if you wait 2 weeks, it'll be just the opposite. The side that's facing us is the lit up side, and the side opposite is the dark side. So there's not a side that stays the dark side. But you can always say any moment there's a dark side of the moon. Lord and Lee.
So the moon doesn't spin around in itself like the Earth does?
It does not. It is locked with the Earth. So in the time of one sidereal month, it will do one rotation because it's locked on us. So as we view it, it doesn't appear to rotate.
Why do we rotate but it doesn't?
It's because of it's close to us. We have a pretty strong gravitational pull, and it wasn't perfectly symmetric. This happens a lot. If we look at the orbits of the Galilean moons of Jupiter, they have a very, very interesting resonance. They have each, if you start with the inner one and you go out, you multiply by 2 to get the period so that they have a 2-to-1 resonance. One does 2 orbits for the time the other one does 1. And those are set up for the same type of reasons, because they're not perfectly symmetric, or well, in that case, it's not perfect symmetry, because the gravitational forces push it into that. Furthermore, when you look at the rings of Saturn, you know how Saturn has rings, it's not just a solid disk? It's because of a very similar effect. Mercury is the most interesting. Mercury has what we call a 3-2 orbital resonance. It does 3 rotations in the time it takes to do 2 orbits. The reason it's a 3-2 resonance is because Mercury has a fairly elongated orbit. It's not perfectly circular. And so you can't have a constant rotation because its speed changes in the orbit. And so gravity has found a lower energy state by having that 3-2 resonance. It all comes down to, everything in nature comes down to what's the lowest energy, and things work toward that. Okay, a couple terms here. Umbra means shadow.
Like an umbrella.
Well, yes, which is shadowing you from rain, or if you call it a parasol, it's the umbrella is shadowing you from the sun. And so the place where you have complete shadow here in this picture, that's the umbra. Now you can see there's a region out here that's partial shadow. Penumbra means the part right next to the umbra. Just like, there's that skit, the penultimate supper. Supper before the Last Supper. And penultimate, next to last. Ultimate, last. Penumbra, next to the umbra. So the umbra is partial shadow. If you look in this picture, it has nicely drawn. The white lines are going from one side of the sun to the opposite side of the moon. And the, where's the, it doesn't have all the lines you would have. It would also be nice to have the line that goes like, it only shows the end part of these lines. But you have complete shadow inside the red here and partial shadow inside the white. And so everything in this region here is in the penumbra, but only that point are you in the umbra. So anytime you're in the penumbra for a solar eclipse, you see a partial eclipse because you're seeing part of the sun blocked. But if you're in the umbra, you see the full eclipse, you see the full sun blocked. Now coming up, there's another slide, I'll say it now so I can skip over it when I get there. It turns out that if you could choose different things, either random chance if you don't believe that God did this, or God said it this way because it's kind of cool. The angular size of the moon, it takes up about an angle of 1/2 degree. The angular size of the sun is also right about 1/2 degree. So if you look at the sun and the moon, they're about the same size as we view them. Not actually the same size. The moon's much closer, hence it's much smaller to take up the same angle. But because they're just about the same size, we can have the moon pass just in front of the sun and just block the sun. But sometimes the moon is closer to the earth and sometimes it's farther. Sometimes the earth is closer to the sun and sometimes it's farther. And because those sizes are almost exactly the same, there are times when the angular size of the moon is smaller than the angular size of the sun. In that case, the moon cannot block completely the sun. That's like I take my finger, I put it up here, and I cannot completely block Dylan's shirt, right? His chest is wider than the angular size of my finger. Haha. It's the same thing when you have just the right distances. When the earth is farther from the moon but closer to the sun will take up a bigger angle and you'll just block the center part during the eclipse. We call that an annular eclipse. And I think I mentioned my wife and I went and saw the annular eclipse in Santa Fe on the way to California to get married. So she wasn't my wife yet. Which is very cool, I thought. Tie in some astronomy. Then we went to the Barringer Meteor Crater so we could see where a big rock hit the earth. And a cool astronomy thing. And then we went home to California, celebrated my grandmother's 100th birthday, and 3 days later got married.
Oh, wow.
Yeah, my grandma's still alive.
Yeah, wow.
Unfortunately, for the last 15 years, she hasn't known anybody, but she's alive. You take what you get.
115?
No. She's 103 now. I've only been married 3.25 years.
Oh.
No, for 15 years, she hasn't known anything. Like, her brother came to see her for her 100th birthday, and after he left, she was like, "Who was that?" "Well, that was your brother." "I have a brother?" "Yeah." "Well, nobody told me." It's sad, yes. Okay. I know. I'm halfway there. Well, not really. I've got another year and a few months before I'm halfway there. Okay. We were asked about the eclipses occurring. This is a picture of the paths as seen on the Earth for all eclipses from 2001 through 2025. Now, if you look at these here look super big, right? They're not super big necessarily. The map, to make a spherical Earth and flatten it out flat, it turns out it takes a much bigger space on the flat than it actually does on the spherical Earth's surface. Question first?
We'll comment on that. Also, we have to take into account that at the poles, the shadow's going to hit
Yeah,
it.
you've got the glancing angles as well. That's right. Kendrick?
So, I don't have my glasses on, but in essence, in 2017, there should be an eclipse right here in Nebraska.
That's the one I was talking about, yes. It's going to happen. It's something like August.
Date.
Oh, it says right there, August 21, yeah. So August 21, like 3 days before school starts, you can just go down to like Nebraska City, 30 miles away, and you will be in the path of totality. We're going to be very close to path of totality here. But I won't have any students here.
I'll be here.
All right, you and me.
Let's do it.
All right,
I'll contact you. I'm actually not joking. I'll probably be here.
cool enough. We're going to have the glasses so we can look at it.
I'll come to you.
All right. Hey, I am actually serious. If y'all are interested and you're around, contact me.
That's something worth seeing.
I'm definitely going to be going somewhere to see it better.
Can
Tell me in
you get
Nebraska?
Can you get us out of classes for that? Or?
It'll be before school starts.
School starts, so
So absolutely I can get you out of classes.
then I'll go.
All right. Okay, so yeah, you saw that one that's recent. Now this one here, it's another one that crosses the United States, which is totally cool for us. But yeah, it doesn't pass through Nebraska.
That's the Texas.
Yeah, well, everything passed through Texas, it seems. Satish.
So these lines, are they documenting when it's at totality or just?
Anywhere in the blue, you will have a total eclipse. The times for the eclipses vary. You can go like NASA has a really nice site for what time will the eclipse start and what time will it end for any location. So you can figure out exactly when you need to be in Nebraska City, for instance, if that's where you're going. Or we're more likely, since Ken's from that area, going to go down to St. Joseph area. And so we can look and see exactly when it'll start and when it'll end in St. Joseph. The reason to go to St. Joseph is you're right about the longest totality.
Oh, okay.
You got another question, Kenny?
Oh, yeah, like the wider fast.
Yeah.
Can you really explain that? Like,
Well, partially. There are multiple things going on. The farther away you get from the equator, the smaller the area for the same width line. And so you have to make a wider line to cover the same area if you're closer to the poles on the flattened out map. And also, if you're on that part of the Earth, the shadows are elongated because you're looking at a sidelong.
because it's on the top, which is more flat.
Yeah, well, not necessarily because it's more flat. You have something like this and you have a shadow that takes up this much area. It's a bigger region on the surface of the Earth there than if I had the same width hitting here. So that also makes it look wider. Right? For the same width from there to there, it's going to take up more area here because of the hitting it at an angle like this. So you're going
Oh, gotcha.
versus.
Yeah.
Okay, but these do accurately represent the actual width that it will be covering. And the wider the region, the better it's going to be. So if you like zoom in here on the one we'll be seeing, you can't see much variation on width, but it is about that mark there That's where it's going to be the most impressive. And now, truthfully, St. Joe is about here. So we're not getting all the way to that, but it's pretty good. Whereas Nebraska City is, well, on the bottom part of that mark. My pen goes really big because I'm really zoomed in.
Yeah.
But I just wanted to show that's not the center. It's at the edge, but it's in there. And Lincoln is outside of it. So Lincoln, you won't see. Wow. My fingers, well, I'm really zoomed in anyway.
If that line's at all accurate, though, it's just barely outside of it.
That's right. It is. It's just barely outside of us. So we're going to be really close. In fact, what you will get at its closest is what they call the diamond ring effect. When you're blocking the sun and you have just a tiny bit visible, you have something really bright and then nothing around it. And so it looks like kind of like a diamond ring. The diamond ring effect is when you have just that little bit of sun you see, and compared to everything else, it's ultimately bright. Whereas, I mean, normally the sun looks really bright, but we don't look at it. Here you're looking at it because, oh, it's all dark, except for that super bright spot.
And then you go blind.
Yeah, well, you win some, you lose some, right? Oh, no, seriously, Galileo, we're going to talk about him. Galileo, he didn't invent the telescope, but he was the first person to use the telescope to systematically study the heavens, including the sun, hence damaging his vision permanently. You know, not the best move. Of course, I'm stupid myself. When we had a partial eclipse that was visible here in Lincoln a while back, I went out there and we had these glasses you can wear so you can look at the sun. And I was using the spotter scope on my telescope to look at it. And I put the filter on the eyepiece side where the light is focused. And so I'm looking through it. Oh, yes, that focus line melted a hole in my filter. If I put it on the other side, of course, it would have been no problem. But the light is concentrated. Yeah, we all make mistakes. We live and we learn. And I can still see. I averted my gaze. I will finish here with the eclipses and then we'll take a break. The Saros cycle is a cycle of repeating eclipses. It was discovered by the Chaldeans or Chaldeans. Y'all heard of these folk, right? I mean, we've all studied Daniel.
They tried throwing people into lion's den and all sorts of stuff.
They did things like that. They noticed long, long ago that every 223 synodic months, the eclipses repeat. Now, 223 synodic months turns out to be 18 years, 11 days, and 8 hours. So if you know when an eclipse occurs, you know, where that stripe hits, you know that exact same geometry is going to repeat in 18 years, 11 days, and 8 hours. Well, 8 hours is exactly 1/3 of a day. And so the position is going to shift 1/3 of the way around the Earth for each time it repeats. So, for instance, we have this eclipse that's going to hit here August 21, 2017. You go 18 years, 11 days, 8 hours, so that's going to be, you know, September, whatever. 30 days has September, April, June. So let's go to September 2, I think that comes out to be. Or, yeah, I didn't do the calculation. In 8 hours, it will reoccur in 17, 18, 2035. But it'll be 1/3 of the way around the Earth. You wait another Saros cycle, so another roughly 18 years, it'll be another 1/3 of the way around the Earth. And if you wait 3 Saros cycles, which is going to be 54 years and a month, it'll be back here in Lincoln again. So, you know, every 54 years and a month, there'll be an eclipse here.
Excellent.
Yeah, good to know, because you'll be alive in 54 years and a month.
I hope not.
Well, in heaven or here, you know, it should be one of the two. Yeah. When I was your age, I never planned on living past 30, so I can understand. Life is bad when you get old. After I tore up my shoulder, it's never been the same. Then I had the blood clots. It got worse. Okay, so this Saros, oh, look, here I had done the calculation. Every 54 years and a month, well, in 34 days, you have the eclipse to reoccur. Why do we have this cycle? Because the eclipses occur based on geometry of the moon's orbit around the Earth and the Earth's orbit around the sun. And so based on the periods of those two, you get this Saros cycle. And it has to be exact synodic months because it can only occur when the moon is crossing the ecliptic. Hence it has to be, months. Okay, I've gone through 1/6 of the slides. I prepared a lot more slides than I ever hoped of getting through.
That's okay. We're going to be here for a while.
Well, we're going to take a break soon. But we only have like 2 more slides. I want to finish the eclipses and then we'll take a break. This here goes to a question that somebody over on my right-hand side asked last class period about the orange color of the moon. My right hand, your left hand. I know you're looking around and say, who could it be? Here's a picture of the orange color of the moon. I looked through the slides I've used in the past, and somehow this picture got stuck on a picture of the moon during a solar eclipse as well. And I'm like, what? The moon during a solar eclipse? Nah. Anyway, this here is what it looks like when you have the moon in a lunar eclipse and you have the light from the sun is blocked, so it's in shadow. But as I talked about, that bending of the light, the refraction through the Earth's atmosphere, makes light that goes through that skin of the Earth's atmosphere come over and hit the moon. But it's reddened because the blue light has been scattered away and the red light is what made it through. And so that's why it's got the reddish, bloody color. And you can see this if you're somewhere dark. I was at a Giants game in San Francisco just before they before they moved out of Candlestick and went to Pac Bell Park. And there was an eclipse. You could not see a darn thing of the eclipse moon because there's so much light. Of course, I was out there ice skating once in an ice skating rink in San Francisco. You could only see 3 stars in the sky. Yeah. Look, honey, it probably was Jupiter and, not even stars. Okay. I just wanted to show that picture to go with it. And I know we're getting close to my stopping point. I'm going to go right past here. This here is just like what we've already seen, right? Yep. So there's no reason to stop there. And we stopped at this picture already. And the calendars. Lots of calendars for lots of regions. You know that we have things like the Chinese New Year. Chinese New Year is very different from our New Year. Why? Because, did you get my email?
Yeah.
Is it clear?
No, it's fine.
Oh, okay.
I was just going to let you know.
Okay. Jeez. You gonna come play football on Sunday?
Yes.
All right.
We'll have a good class. No.
Reese came to tell us, we ain't going outside. The Chinese calendar is based on lunar cycles. And I don't remember. I didn't look it up to renew myself. But they have a sequence of when the new year starts. And it's always going to be with a new moon when they start the new year. And they have a way of determining which new moon it's going to be. And after they get so far off cycle, they just adjust the number of months in a year to get back on cycle. So they have essentially leap months. The Jewish calendar is similar, using a leap month to stay on cycle. Now we have our calendar, and it's fun to look at the names of the months. Okay, January. Where's the name January come from? It comes from Janus. And then we have February. I don't remember where February comes from. Anyone else? Comes what? Yeah, I'm like, what? March. Where does March come from? Mars. April. I don't remember that either. We've not gotten to the part I'm interested in. May, I don't remember. Yeah, thank you. June. July.
Julius. I guess it is.
Julius Caesar. Augustus Caesar.
And then we get to the ones I want to focus on. September. What does that mean?
7.
Don't argue with me.
He didn't make them up fast. Come on.
Okay. But we all know December's the 12th month, November's the 11th month, October's the 10th month, and September's the 9th month. So where does that come from? Truthfully, as far as I know, no one knows. They just assume that there must have been a time when they either started the year, out here, or when they were running on a 10-month system. But these other ones have been over time in history renamed, and people like Julius Caesar grabbed one for himself and said, hey, let's add an extra day because I'm important. So it gets longer by one. Where are we going to take that day? February didn't need it. Caesar Augustus. Hey, I'm going to take a month, name it after me. I was after Julius. I'm going to take one after Julius. We need an extra day for it. Where did we get that day? February didn't need it. And so February just kind of got robbed.
So then out of December, I never 31.
Nah, I don't know. I don't know. I just know how that came out. So to me, that's very interesting. Some historical perspective. And days of the week. I was going to say, how many days of the week do we have? I think everybody knows that's 7. Why do we have 7 days? Nobody knows, but here are some options. I personally believe it's this one. Okay? That's the one I adhere to. The Bible says, for 6 days the Lord created heaven and earth, on the 7th day he rested, wherefore the Lord blessed the Sabbath day and hallowed it. Right? We have a weekly cycle set up in the Bible. And certainly the Jews followed that weekly cycle, and it is believed that based on the Jews and the Islamic cultures, remember the Islamic culture is also Abrahamic. That is, they're descendants of Abraham as well, so they would have the same traditions and histories regarding creation. And Christians, obviously, were from that. So we have promulgated that 7-day week. There have been places where they've tried other things. But that's the one I believe. Other options are that the days of the week are named after the 7 prominent objects that we're seeing in the sky. So you have the sun for Sunday, the moon for Monday. I don't remember, obviously, yes, these are in order. Tuesday must be Mercury then. Wednesday, Venus. Thursday, Mars. Jupiter Friday's Frida. So that's not working out perfectly. It depends on what language you look at the names as well. And of course, Saturday for Saturn. And so that's a strong theory that the names of the days were chosen for the major objects that were seen in antiquity, and they set the week cycle to match the number of objects they saw in the sky. Another one is that simply they took the quarters of the month and said, let's make 1 week for each quarter. There's no accurately known origin for the 7-day week, but I believe that one. Okay, let's take a break. We'll come back at 9:20. And I'm actually going to stop this recording, and then I'll start.